Thank you, ma'am.
Yes. So, thank you so much to everyone. The introduction was very nice. Thanks to you, ma'am. Hope my voice is audible.
Yes, ma'am. It's very audible.
Yes, ma'am. Yes, ma'am.
I thank Dr. Muralidhar, sir, who is the head of research, and the principal of Gayatri Vidya Parishad College of Engineering for Women. I thank both of you for this invitation for this event, which is sponsored by ANRF. And before starting the talk, let me just start with a few of my works which I have initiated in quantum computing. The works are already published in SCI journals. So you can go through those this through my Google profile. And maybe it will inspire you to work in this particular research domain. And one more good news is today I had one of my patents granted. So today is a good day for me actually. Okay. So with this few words, and again, I thank the organizers and the entire team for organizing this event. It takes a lot of effort to handle an event which is 5 days and to have a participant, I can see almost 100 participants are there. More than 100 participants are there. So kudos and congratulations to the organizers. Now let us go to the topic now. So I hope the screen is visible now.
Yes, ma'am.
Yes, yes, ma'am.
Okay. So the topic we are going to see a few insights on is quantum resilient secure architectures for 5G, 6G networks. So why 5G, 6G networks is because all of us are depending on wireless network technology for all the communication, whatever data transfer is happening. So that is why I am concentrating on 5G, 6G networks for today's session. So before starting into the more technical aspects, let us just go into what is a quantum threat landscape. We know that quantum computing and quantum algorithms can break the existing cryptographic algorithms, right? So almost all the algorithms existing today can be broken by the quantum algorithms, such as the Shaw's algorithm and the Grover's algorithm, which we all know. And our main aim is we should have a quantum secured post-quantum 5G, 6G networks, which will have quantum safe security mechanisms. As of now, our wireless communication systems are not built with quantum safe security mechanisms. And we have to stop this harvest now, decrypt later. So harvesting now is the data is being stolen by the eavesdropper, either using AI, it can predict the data, or using any other method. So the data is harvested and it is decrypted later. So these type of attacks are increasing now, which increases the problem of cybersecurity risk. And because of these reasons, post-quantum cryptography is very much essential for the secure communication. So if you see the table that is given here, it shows the classical algorithms. We know all these algorithms, very famous ones, RSA, which is already broken by quantum algorithm. Similarly, ECC is already broken. Diffie-Hellman is vulnerable, and ES128 is an algorithm. It's a classical algorithm. Due to the quantum impact, it has very reduced security. So RSA and ECDH. ECDH is nothing but Diffie-Hellman. It will be vulnerable to very powerful quantum computers, which are running the Shaw's algorithm. And we know that nowadays Open RAN. So Open RAN is nothing but Open Radio Access Network. Also, the 5G, 6G, the telecom infrastructure is based on this ORAN architecture, that is Open Random Access Networks. This has multi-vendor interfaces. So all these interfaces are open interfaces, and multiple vendors are providing the softwares and hardware for this ORAN interface. So, and since the telecom infrastructure is spread over a huge area, there is a large attack surface. So anywhere in the cyber system or IoT device, the attack can be done. So the large attack surface is also a very big problem as far as 5G, 6G networks are concerned. And as similar to the hardware, the protocols, the open radio access network protocols are also vulnerable to quantum attacks. And what is happening now is the key. There is a very weak key exchange that happens, which is not at all resilient to quantum threats. So we need to have solutions for this. So that is why we go for post-quantum cryptography. And we know what post-quantum cryptography is. So we use the short form PQC, right? So PQC will provide the security against the future quantum attacks, quantum computer attacks. And we know that all the algorithms, the standardized algorithms are being provided for secure communication and authentication by the NIST. NIST is nothing but the National Institute of Standards and Technology, which is US based. So they provide the NIST cyber security framework. And this framework provides the organizations, businesses with a structured and flexible best practices to manage and reduce the cyber security. So all of us should be aware of NIST and what all the standardized algorithms that NIST is providing for cyber security. Now, the most important concept is quantum key distribution, which is the base of this PQC. So quantum key distribution, I think all of you are aware of it now, which enables the secure key exchange using the properties of quantum mechanics. So, and here, what is it? Normally, pseudo-random number generators are used. But the problem with pseudo-random number generator is that it has a predictability. And due to predictability, the eavesdropping is possible, right? And also QBER. QBER is nothing but a quantum bit error rate. And the quantum bit error rate is calculated when we transfer the quantum key distribution using PRNGs. But the problem with QBR is that QBR alone cannot fully measure the key security. Okay. So these are few drawbacks of using PRNGs, that is pseudo-random number generators, and QBR alone for measuring the security of QKDs. What is more relevant in today's time is entropy-based evaluation, which is required for the stronger security assurance. So if you see this diagram, now this is the basic diagram of quantum key distribution. Of course, it looks little big, but the concept is very simple. So I think all of you know about the quantum key distribution. How many of you know here what is the main concept? Can you please put in the chat box? So if you are not, see, I can explain little bit, but not fully. But if you don't know much about QKD, there are a lot of YouTube videos which explains the basic concept of QKD. You can go through that. So as I already told, you have the quantum key distribution. It is used for distributing the key between the sender and the receiver. So normally in the threat model, we call this sender as Alice and receiver as Bob. And here we use a quantum number, random number generator, not a PRNG. So this we call as a QRNG. You see the first block, which is the quantum random number generator. And this is quantum random number generator will generate the quantum bit in a random way. And this will be sent through the free space, or it can be sent through optical fiber. And it will be having a diagonal polarization or rectilinear polarization. So based on that, you have the basis. So whether the basis is rectilinear basis or whether it's a diagonal basis. So the data will be sent as a qubit through free space or through the optical fiber as a photons. And this will be then received at the bob, and the bob will be also having a set of bases. So after transmission, what happens is both the users will compare the selected bases, whether it's a rectilinear or diagonal, over a classical channel, and it will retain only the matching results through a process called shifting. So if you see, there is a block called as shifting. So why this block shifting is used is it will have the selected bases will be compared, and it will be retaining only the matching results through a process called shifting. Then after shifting, we have different other methods, blocks. You can see error estimation is there, error correction, then privacy amplification and key verification are also performed to generate a highly secured shared secret key. So we will see a few things about these blocks in the coming slides. So these are the main blocks that involved in QKD. And as already told, it uses the concepts of quantum mechanics. So QKD will provide the unconditional security. Due to this, I recommend that all of you please watch the YouTube, because a lot of videos regarding the quantum key distribution is there. And this will give you a very clear idea, because through this theory, I think it is very difficult to understand. But this is a very important concept that you should go through. So is the slide changing? Yeah. So the most important protocol for this quantum key distribution is, there are many protocols. So we have BB84 protocol. I don't know. I think many of you would have heard of BB84 protocol. Then you have E91 and B92. So as already discussed, Alice will go through the sender data bits using the quantum channel, and it will be received to Bob. That is the receiver. So here BB84 protocol will enable the secure communication between the sender and the receiver. And this method, this QKD will help to detect the eavesdropping immediately. So not even like, there is no case in which you cannot detect the eavesdropping, because you are giving rectilinear and diagonal basis. So whenever there is a small change in the key detected by Alice and Bob, then it will stop transmitting. Alice will stop transmitting the data. Now, what is QBR? QBR is a main term that is used to calculate the efficiency of the quantum key distribution. So QBR is nothing but the erroneous bits received by Bob divided by the total bits transmitted by Alice. So this is QBR is a very important parameter when we evaluate the security of any channel. So in PQC, what are the main challenges we had? We have overcome that in QKD, because QKD uses a quantum random number generator. As you saw in the previous diagram, here the first block is a QRNG, not a PRNG. So what happens is, if you use PRNG, entropy degradation happens, but QRNG improves the entropy. We will see how it improves. And information leakage during post-processing can be removed by QKD, because information leakage, to avoid information leakage, we use a concept called as privacy key amplification. So this privacy key amplification step, that is also there in this block diagram. So privacy amplification, you can see after shifting, error estimation, error correction, you have the privacy amplification. So in this step, you can see that it will avoid the information leakage during post-processing. And so what are the requirements of a good QKD? It will be high entropy and very good randomness and very secure final key at extraction. So different existing solutions are there. And different analysis techniques are also there to estimate efficiency of QKD. So you have the entropy-based security analysis, or we have the privacy amplification techniques to improve the security, or we can evaluate the Shannon entropy and min entropy to calculate the security analysis of the existing QKD. So these are the different methods that we use for security analysis. So if you see here how the random number generator is integrated with the server. So the QRNG is a hardware, and then you have to we have to integrate it with the server. And then through MLKEM, I'll tell you what is MLKEM. It is a key generation algorithm. So the QRNG based key generation will be feeding the MLKEM with true quantum entropy. And from the MLKEM, it will go to for the private key, public key, shared secret, and the ciphertext. So if you see here, what is the difference between PRNG and QTRNG? So QTRNG is quantum true random number generator. So PRNG is deterministic, whereas QTRNG is true random. Of course, we know that quantum bits are very much random in nature. Even we cannot estimate the value in one check, right? So if we go for testing, the value of the qubit will get changed. So it is truly random in nature, which makes it very useful for cryptographic techniques. And PRNG can be predicted, whereas QTRNG is very difficult to predict due to quantum entropy. And hence QTRNG is highly secure. Uh, Okay. So are you able to see this diagram? Is it clear? Can you all please respond?
Yes, ma'am.
Okay. So this is an architecture. So this architecture is used for an entropy resilient quantum key generation. I think someone has unmuted the audio there. Okay. So here, if you see the cyber physical system, obviously it will have sensors, digital twin, physical process, IoT, and all those things. So for these data will be taken and it will be coded, okay, coded as a qubit by the generator. So this is a unique architecture. In this architecture, if you see, they are using both PRNG as well as QTRNG. And both of them are clubbed using the XOR, randomness fusion. So this XOR randomness fusion will help to increase the entropy actually. So once you have the PRNG, QRNG bits generated, the channel noise and QBR estimation will be done. And after this, both of them will be XORed. And then the evaluation of the Shannon entropy and min entropy will be carried out. And after this comes the next step. If you see the last step, you have the privacy amplification. And after privacy amplification, the secure final key will be generated. So this is the normal step that we used for generating a high entropy cycle. So this is the architecture that is normally used in ORAN, that is a random access network, open radio access network, to generate the highly secure key. So this, if you see here, this is also just the more in-depth view of the this thing. If you see here, can you see the block diagram? It is little small, but I'll try to explain it. So here what happens is you will have the CPS generated sensor data. And if you see the left-hand side, you can see that so the sensor data, it can be from IoT sensors inside the automobile or from a solar panel or from an electrical station. So all the sensors data, it will be encoded into quantum states. So the data will be converted into quantum states. If you see left-hand side, I don't think I need to tell you what is a quantum state. You would have studied it through the first 2 days. Now, after the data is converted, the BB84 protocol will generate the secure keys. And for the BB84 protocol, it will use PRNG and QTRNG. And XOR fusion, if you see, you can see the fourth block, which is XOR fusion. And finally, the BB84 protocol will use the privacy amplification to generate the final secure key. So if you see the left-hand side depicts how the quantum states are looking like, and the right-hand side gives you the block diagram of the entire architecture. So now these are the mathematical terms. When you go for the analysis of any security model, it is very important that you have to go through the analysis, right? So simply we cannot tell that our model is secure. We have to prove it mathematically using equations. So the normal terms that we generally use are the quantum measurement outcomes. Then we have the Shannon entropy to be calculated, and the term number of qubits, which is very important, which normally we use the letter Q, and number of measurement shots. So measurement shots is the number of repetitions per qubit that is needed to generate the bit sequences. Okay, for example, 1,000 shots will be there, or 2,000, 5,000. So number of repetitions per qubit to generate the bit sequences, that is called as S. S is nothing but the number of measurement shots. Then next mathematical term is QBR, which we already told the equation. So it will help us to estimate the channel quality indicator derived from the mismatched quantum measurement outcomes. So that is number of erroneous bits divided by the total number of bits that is being sent. Then there's a security parameter epsilon, which is a statistical security bound defining indistinguishability from a uniform key. And then entropy matrix is there, H and H min. H min is minimum entropy matrix, and normal entropy is H. And we also have the Shannon entropy, right? And then there's a universal hash function. This universal hash function is used to generate the final key during privacy amplification. So many hash functions are there. We can use any of the universal hash function to generate the final key. As I told you, privacy amplification is for minimizing the leakage of information. Okay. And then the final key length is denoted by small l, which is the length of extracted secure key after the privacy amplification. So this block diagram, I hope it is more clear to you now. Here we have, because I have given you enough basics so that you understand this diagram. So towards the left hand side, you can see the classical key, generation key. And towards the right hand side, you can see the quantum key generation blocks. And using the BP84QTRNG and BP84PRNG, you are XORing it and then calculating the entropy analysis, Shannon and mean entropy, all those things. And finally going to the privacy. So here you can try different combinations. You can even try the classical generation key alone with BB84, or you can try the quantum key generation QTRNG with BB84 alone, or you can try the hybrid also. You can just analyze which is better. So that will be one interesting thing. Now, when you want to implement some architectures, generally we can go for a few of the tools. So one is the IBM Qiskit. Then we have AER simulator. I think AER simulator, all of you can just Google, the link will come. So there is no difficulty in this because all are open source. So there is no problem at all. You don't have to think that we don't have the tools to work. Then Python, obviously everyone works. And you can try with a few parameters like 8. You can start with 2 qubits or 4 qubits and generally expand to 8 qubits. And 1,000 shots is, I told you, this is the number of repetitions that you do for the key generation. You can increase it slowly. And whenever you do a key generation, the channel will have noise. So some noise model you should be explaining. So you should be adding the noise. I think you all would have done image processing. You have image, you add noise, right? So it can be salt and pepper noise, any type of noise. So similarly in the quantum channel also, when we do the analysis, we need to introduce the noise. So just one example. So many types of noise are there, but we cannot put everything since it will get confused for you. So I've just put depolarizing noise. This depolarizing noise model is actually, just let me tell a few words about it. It can be added with the gate error. You know that quantum gates are there. So we can add this depolarizing noise with the gate error probability and qubit readout error probabilities. And there are three types of depolarized noise. That is bit flip noise, phase flip noise, and bit plus phase flip noise. So three noises are there. Okay. So one is bit, because we know that qubit is represented by bit and phase. So one is bit flip noise, which they normally call as X error. Then Z error is the phase flip noise, and Y error is the bit and phase flip noise. Okay. Not going much into it, but you can just Google and find out the more basics. And you can have the hardware computation also. So how will you do the hardware computation using IBM Qiskit? You can run your code for some time. You cannot run your code for more time. In open source, you can run your code for some time, which will be more than enough to get our results, initial results. So this one example graph I have taken here, how to find out the QBR analysis. So are all of you able to understand what I'm telling? Just to stop in between. Hope all of you are able to follow. In any doubts till now, you can ask. Okay, so I assume that I'm not able to see the chat box here. Sir, anyone has have messaged any doubts in the chat box? Okay, so since there are no doubts, we will continue. So this graph is along the x-axis, you have the rounds, that is the shorts. And along the y-axis, it is given the QBR. So QBR versus rounds is plotted for different types of key generation. So BB84 PRNG is the blue line. So you can see that QBR is high for BB84 PRNG, whereas BB84 QTRNG, it is the QBR is in medium 0.08, and BB84 QTRNG, this XOR1 is the green one. So there the QBR is low. So what we can understand that if you combine both the methods, then your QBR, that is the number of erroneous bits divided by the total transmitted bits, is less. That means error of transmission is less. So that is what we can understand from this analysis. Then, as I told you, with QBR alone, we cannot have a security analysis. So we go for the Shannon entropy analysis. So can any of the participants decode this graph and tell which is better? So any 2 minutes I'm giving. Can you please decode this graph and tell which method is better? Or you can share in the chat box also.
Hello, ma'am.
Yeah, yes.
I think the blue graph should be the better one because lower entropy is better.
Okay, thank you for responding. Is there any messages in the chat box? I'm not able to see that.
Ma'am, I think the minimum entropy has, which is AP84 PRNG, which has a minimum entropy of 0.60, is much better graph.
Okay. So let me explain this concept. Any other answers? We'll wait for one more second.
Yes, ma'am. I feel XOR is better because even with the
Okay.
shorter number of rounds, we can see the entropy is more.
Yes. So what is your
And the
name, ma'am?
confidence is more. That is
What is
what
your
we
name?
Rekha.
Yeah. So Sureka, ma'am, congratulations. The answer is correct. So what I would like to tell is thanks to all the participants who responded. So it made me get assured that all of you are listening. Okay. So whenever we have this entropy, more the entropy, the better security actually. So the entropy is also a measure of the randomness. So this is a min entropy based randomness assessment. So if you see here, QTRNG XOR has a min entropy value of 0.96. So that means that it is having a better security against adversarial guessing. And the equation that we use to calculate is h min of x is equal to log to the base 2 max p x equal to x. What is this capital X and small x? I'll tell you. This is the small x is the most predictable outcome. That is the outcome that happens most, okay, most number of times. So that is the small x. So probability that the most predictable outcome. So this equation will, what this equation will do is it will measure the worst case unpredictability of a random source by considering the probability of the most likely outcome. Okay. So higher min entropy means the security is better. Now we'll go to the next analysis. So this is the next analysis that we have. So I told you this is the last step, that is the privacy amplification. And what can be infer from the privacy amplification results? So here, this is the most important security equation because since it is the last stage of the quantum key distribution and key generation. Here, this L stands for the final secret key length, and epsilon, as I already told you, it is a security parameter. And H min of KF is the available secure randomness in the fused key. Fused key is the one that is XOR key. And there's the next term is leak of EC, leak underscore EC, which is the information leaked during the error correction. And 2 log 1 by epsilon is the security margin to guarantee the secrecy. So this is how you calculate. So we have the terms L is less than or equal to H min KF minus leak underscore EC minus 2 log to the base to 1 by epsilon. Here, epsilon is the security parameter and small l is a final secret key length. Okay. Here, KF is nothing but the fused key length. For example, just for an example, I'm telling, suppose we had h of KF as 1,000 and leak EC as 100. Then and your log of 1 by epsilon as 60, value you will get as approximately 840. So L will be length of the final secret key will be less than or equal to 840. So that means that from the 1,000 bits that is transmitted, only 840 bits will be safely used as the final secret key. So that is the assumption. Okay. I'll repeat once again. If H min HF is 1,000, and the EQT is 1,100, and the next one log 2 1 by 2 log is 60. So finally you get the secret key length as L less than or equal to 840. So that means that out of the 1000 qubits, only 840 qubits will be used. So this is what the analysis helps us to do. For example, we will get the value as 63%. Just for an example, I'm telling. It can get it as, if you improve your method, you can get the key retention to be 83% also. But you can get different values, 84%, 85%, 63%, all these you can get it. So this table shows how you compare the different parameters. So PRNG QKD is, Shannon entropy is less. Minimum entropy is 0.60, key retention is 0.45. So the key retention is highest for QTRNG QKD, which is 0.68. And but QKD XOR has Shannon entropy better and min entropy also better. But if you see the middle one, QTRNG QKD is the considered as best as far as results are concerned. So QTRNG QKD has good Shannon entropy, good min entropy, and a very good key retention. So this is just one example. Now, since we went through all the basics, we'll go for the PQZ architecture. PQZ architecture for 5G networks. So we know that obviously your telecommunication networks are huge, and as I told you, it has a very large surface. And so moving towards open radio access network, the problems are open interfaces are there, then multi-vendor interoperability is there because multiple vendors are involved in this. Then again, AI-driven network automation is also happening. In this case, quantum computing will threaten the current cryptographic systems, right? So, and since the key challenge also we need to overcome, that is harvest now and decrypt later. So this is the Open RAN architecture. You see here, this is the general architecture of an open radio access network. So if you see the main components, you can see what are the blocks that you can see is ORU. ORU is a radio unit. And the ODU, that is the distributed unit. So the OCU is a centralized unit. So each unit has its own functions. So this is actually based on a cloud. Okay, so cloud, and it is a mostly software defined framework. It is a software defined framework. And this actually disaggregates the traditional mobile network into modular networks, into different hardware and modular network, so that each company can give their modules. So there are no interfacing issues due to this. So it will disaggregate the traditional mobile network into hardware into modular and virtualized subcomponents, which are linked by open standardized interface. So this open is a problem here. But it is an advantage also. Open interfaces are a problem in terms of security, but open interfaces are very good for the flexibility of the telecommunication networks. And another very important features of open radio access network is the cloud architecture, and AI-driven optimization is also a very important property of open radio access network. Now, before going into this, we can have the different functions of different blocks here. And this SMO is the most important block. If you see SMO, the full form is Service Management and Orchestration Unit. So SMO is the Service Management and Orchestration Unit. Now, this radio unit is a unit that processes the radio frequency signals. Okay. So as you know that the data is transmitted as RF signals, right? Your voice, in the video data, everything is transmitted through free space as RF signals. So it will transmit and receive the wireless data. So the radio unit, the main function is to transmit the radio frequency signal, and it is deployed directly at the cell site. Then ODU, that is distributed unit, is it will include the upper physical layer, medium. I don't know how many of you are from wireless communication EC background, I think this will be more understanding to them. So already we have studied about physical layer, MAC layer, and radio link control layer and all. So this ODU will manage all these layers, and OCU, which is a central unit, so it will manage the non-real-time protocols like the packet data transmission, then the resource controlling, radio resource control, all these will be managed by the DU. DU is the distributed, sorry, the CU, that is the central unit. Now, in addition to this, these blocks are controlled. The transmission happens using interfaces. If you see the diagram, you can see E2 interface, F1 interface, etc. So these are standard interfaces like front hall, mid hall, back hall, and all. So these are different open. These are all open interfaces. And now we'll go to the function of SMO. SMO is used as a centralized manager actually. Okay, so it's a centralized manager that will control the entire RAN system and the underlying cloud also. And it will always have an intelligent controller, which is a dedicated software platform that will help in to optimize the radio resources. So everything is cloud-based here. Now, hope this is the main architecture that we used in almost all modern networks. Now let us go to the next slide. So we know about the hardware now. Now we should know about what are the different protocols that they are using. So this internet protocol security, it is a very important protocol, and this is a secure network protocol. It is used for authenticating and encrypting data packets. But these are classical systems, not post-quantum systems. And this IP internet protocol is used in VPNs. VPN is nothing but wireless private networks. Okay. Then you would have heard of DTLS. DTLS is another protocol that is used in ORAN networks. So DTLS is a datagram transport layer security. So another protocol is MTLS. That is a third point you can see, MTLS. So this is also a security protocol which requires both the client and the server to authenticate each other during a net. So these are different protocols that the ORAN networks are using. Now coming to the algorithms. So what I'm trying to convey is the existing ORAN architecture and how we are going to make them quantum secure. Okay. This ORAN architecture or the DTLS or MTLS, all these protocols are not quantum secure. Any attack can happen from a quantum algorithm at any time, right? So we need to make the quantum secure. So that is the whole aim here. Now, as I told you earlier, MLChem we have seen in the first slide. So let us have an explanation of what is MLChem here. So this is again, this is a NIST. NIST also we already told what is NIST. So this is a NIST standardized post-quantum key encapsulation mechanism. And this algorithm is based on MLW. MLW is module learning with errors problem. And all these are based on mathematical complexity of lattice base. You would have heard of lattice based cryptography. So MLKM depends on mathematical complexity of lattice based problems. Okay. So this itself is a very complex topic. So that's why I'm not going into this in depth. So this will be very confusing if I give you so much information. Later, when you have time, you can go through it. So this is very important. If you integrate it with the protocols, what happens is you can build post-quantum protocols. Okay. So another very important algorithm that is normally used is MLDSA. So DSA stands for this digital signature. Okay, digital signature algorithm. So this also provides a secure authentication and data integrity. And this is based on module MLWE as well as MSIS. MSIS, the full form is Module Short Integer Solution. Okay, that is why it is called as MLDSA. ML stands for module. So module short integer solution problem. Actually, this is a problem that is based on again lattice-based cryptography. This actually involves in finding a non-zero short vector within a specific mathematical lattice. Okay, this is more understandable for mathematicians. Let me not go into much detail about it. But yes, it is a very good research domain where you can work on it. So we know what is IPsec and DTLS. So we are making the PQ IPsec and PQ DTLS. So what is the PQ IPsec? PQ stands for post-quantum, right? So post-quantum protocol and post-quantum DTLS protocol. This will provide the quantum resistant communication. So the MLKM will be integrated along with the secure post-quantum key exchange in these protocols. And post-quantum certificates will improve the authentication and data integrity of the Open RAN interfaces. Okay. So we will go to the final architecture. So I hope you can understand the difference between the previous diagram I showed you, which did not have this post-quantum secure framework, right? It was a basic framework. But now here you have a post-quantum secure framework, right? So can you please tell me what are the differences between this one and the basic architecture that I showed you initially? Can anyone please tell me? Just to check you're not sleeping. So shall I just go to the previous slide so that you will recollect what that slide was? Yeah, so this was the Open RAN architecture, just the components. And what we are seeing now is the post-quantum Open RAN architecture. So this is a post-quantum secure framework for 5G, 6G Open RAN networks, right? So here, if you see here, the protocols and everything, the interfaces, everything is the same, but the communication has been secured with the post-quantum. For example, if you see here, this side, secured with PQMTLS. Here it is secured with PQ IPsec. And this PQTLS, what will this framework do? The PQTLS framework will transition the standard classical internet security architecture to a quantum resistant state. How does it replace? By replacing the vulnerable already existing algorithms. What are those ECC, all those classical algorithms you're replacing with Mr. Standardized PQC. Okay. So that is the difference here. Now, the next point that we have to think of is only PQC enough? Okay. So in this framework, if you see, PQC is given. Okay. Post-quantum secure framework is given. But is this alone enough? No. If you integrate it with AI, it is even more better, right? So that is why we have an AI-based threat detection. Already it is in use. In many secure frameworks, it is integrated with digital twin to measure the threats or to detect the threats well in advance and to take the countermeasures, right? So why not integrate AI security framework also to the Open RAN networks along with the PQ? So you are combining quantum along with AI. So AI will enable the intelligent real-time threat detection, right? So real-time threat detection can be done. If you include digital twin also, it will be very much real-time in the open random access network. And you can also predict the abnormal traffic activities using AI. And if you include federated learning and explainable AI, it can support the secure AI-based decision making. And these are the few advantages. So Malware detection can be done, intrusion detection can be done, traffic analysis can be uh, predicted in future, right? As well as in real time. And AI can be also be used for threat prediction also, not only detection. It can be used to predict the threat well in advance. And technologies that can be used in addition to AI will be federated learning, explainable AI, then intelligent RIC optimization, as well as you can add digital twin also. So this will make your model very proactive, and it will be an intelligent security model for the quantum safe networks. So what are the applications? You have lots of applications. So whatever I discuss now, you can apply it to smart grid, or you can apply it with to a smart city or healthcare IoT, or you can apply it to UAV. UAV, I hope all of us know, drones, unmanned aerial vehicles, defense systems, industrial cyber physical systems, 5G, 6G network. So I have covered only one aspect. You can apply it to others also. So what are the advantages of each technology we have discussed? PQC will give the quantum resistance. QKD will give a secure key exchange. Just to conclude what all we have discussed. So blockchain will give you integrity. Already blockchain, we all know, it is existent for more than 15 to 20 years now. AI will help in intelligent detection and prediction. QTRNG is helpful in giving true randomness, and edge computing which will introduce very low latency. That is, your entire system will be very fast. So, what are the challenges and what are the future scope? So, large PQ post-quantum certificate sizes will increase the communication overhead. So, this is one challenge. The communication overhead will be increased. And the handshake latency is also one cause of concern. So, PQ cryptographic operations may increase the connection and setup time. And hardware should be very improved. The hardware performance has to be improved. New hardwares have to be innovated. New technologies have to come up in quantum computing in order to accelerate the performance of PQZ processing. And standardization issues, because you are combining the PQ security standards with the already available standards, right? Classical. So you are hybrid, you're going to hybrid the PQ with the classical standard networks. So the interface issues will happen, standardization issues will happen. So how to solve it? That is a challenge. And multi-vendor interoperability is there. So that is that is already we discussed, ensuring the compatibility between the different vendors. When you incorporate quantum, post-quantum cryptography is very challenging. So what are the future research directions for what we discussed? You can use it for quantum internet. So future networks will use quantum-based communication technologies, right? Or 6G quantum networks, you can use it. And we can have integration of quantum security to next generation 6G systems that we saw just now. And for secure digital twins, protecting digital twin environment using quantum safe methods, and autonomous cyber defense, AI-driven automation. So a lot of applications that I have listed here. So in fact, quantum cloud security is also there. So thank you. So this is all I have to present today. And hope you got some inputs from my session. So I cannot explain because each concept is very, you have to go in depth. So I have given you a brief overview of what is different architectures that is available. So you can later go in depth and try to do your research. Yeah, thank you. If you have need to contact, you can connect through with me through LinkedIn, or my number and my email is also given. Yeah. Any doubts? Anyone have any doubts?
Ma'am, one question in the chat box. What are the best possible research problems in this area of QC or AI-based detection system, ma'am?
Yes, so this is a very upcoming topic. Is my voice clear?
Yes, ma'am. Yes, ma'am.
Okay, so I have already shown you here in this. One second. So as I told you, this huge. Okay, the applications are huge, and the research is only coming in this area. So you can try for quantum cryptography of image data. You can try changing the data. So how the image can be, encoded as qubits, and then how you can apply the cryptography in that. In quantum key distribution, also you have different protocols. You can create a hybrid system and then evaluate the different security measures. Then integration of quantum with networks that no one has done. So only it is in the budding stage. Similarly, the defense systems, drones, how you can improve the security. All these are very much important domains. And AI, if you see, AI can be used to predict the threat, and AI can be used to think and respond to the threat also. So explainability is very important when it comes to cyber security, because you need to explain to the user what is the threat and why the threat is coming. Because nowadays we are only able to know that this threat is there. So if it is explainable, then it makes us more clear what type of threat and from where and why it is coming. Yeah.
Okay, ma'am. Thank you.
Yeah, thank you. Thank you.
Ma'am, good morning, ma'am.
Yes.
This is Bhaskar from Vidya College.
Okay.
Ma'am, is there any possibility to including the quantum computing in the scheduling aspect? What does the
Yes,
research
yes.
problem of
Yes, yes. See, whatever you are doing, you can run in the quantum hardware in IBM. Have you tried that?
Yes, ma'am. Actually, it is completely focusing on the key generation aspect only. So, how
Okay.
to include
Scheduling,
this
I
in
am
the
not
schedule?
sure. Yeah, scheduling, I have not worked in that domain.
Okay. Okay.
So I have worked only in the quantum architectures and the cryptography. Security, yeah. Anyone, anything else?
No, ma'am, nothing.
Okay,
Everything
okay,
is
okay.
clear.
Okay, thank you. So thanks to the organizers once again for giving me the opportunity, and hope all of the participants will take some points and try to work in their own research.
Definitely, ma'am.
How many of you are working in quantum computing here? Or maybe many of you have started also.
Not yet, ma'am. Some of the faculty are working on that.
Okay, okay.
Now I
So I have
request
also published a few papers in quantum. You can go through it, and you can make use of that also, the participants. Yeah, so thank you.
Now I request Ashwini ma'am to give vote of thanks.
Delivering for your insightful and enriching session on quantum resilient secure architectures. The topics you explained: 5G, 6G structures, quantum algorithms, quantum key distributions, ORAN architecture, NIST standardized algorithms, and so on. And your knowledge have greatly benefited all the participants and inspired us to explore new avenues in research and innovation. Once again, thank you, madam, for your time and valuable contribution. Thank you all.
So I could see that, yeah. So now only I could see the chat box. So few of them have given, can I answer that also? Some research publications in the area of quantum communication. So the best, the venue for your publication, some have asked. So you can go through quantum information processing. So quantum information processing, it is a very good journal. And recently they had an issue of quantum processing in India. So it is a Q1 journal. Even though it is an initial work, I recommend you submit to those journals. You will get the reply with very good reviews. So once you get the reviews, you can work on that. So the editor is a person from IISc. So you will get very good comments. You can work on, revise your paper and your research will. So like that, you try applying for Q1 journals, get the reviews and try to work. Yeah.
Okay, ma'am. Okay, ma'am. Thank you.
Yeah. Thank you. Thank you.
Thank you.